Okay, the coffee machine was slow. So. Um, Let me just start. God, this is throwing me off. Let me just start by, well, first of all, does anyone have any questions from last time? I know we had a lot of chance at the question answer. Okay, so I'm going to finish a couple of things on Clifford algebras, and then we'll talk a little bit about supersymmetry. So let's see, I had a few questions. People were asking a little bit about just these different Majorana, symplectic Majorana conditions and so on. So let's just do one example. So let's do the case where we got a 3-1 signature. And let me write down all the Clifford algebras you might be interested in. So you might be interested in the full real Clifford algebra, 3-1. And that's a matrix algebra over the reals. You could be interested in the real Clifford algebra with the other signature. That's a matrix algebra over the quaternions. You might be interested in the even part of the real Clifford algebra. And these two are the same. Doesn't matter which signature you use. And that is equal to a two-dimensional complex algebra over the complex numbers. Or you might be interested in the complex Clifford algebra. When you complexify, the signature doesn't matter, right? So it's just 4 because I can change a plus to a minus by putting an I in. So if I just do the 4, this is the complex algebra over the 4 matrices over the complex numbers. If I looked at the even part of this algebra, this decomposes into 2 bits. Okay. And if you thought about the corresponding groups, so we have the group spin 3-1, and that's actually the same as SL2C. There's also a group spin, the complexified group, spin 4, and that's SL2C times SL2C. So this is just like you know that the real group spin 4 is like SU2 times SU2. So if you have a complexified group, there's different real forms, this one or this one. They're all subgroups of this complexified one, right? Okay. So you're used to thinking of spinors in 4 dimensions as being Majorana. That's what this one says. People sometimes use chiral spinors in 4 dimensions, but to do that you have to go over the complex numbers. So that's this decomposition. That's chiral. Or if you like, you can also think about a single representation of, or equivalently, you could think of this guy as being the single chiral representation when you go over the even ones. Okay, so the point I wanted to make is when people talk about chiral spinors, they're usually talking about over the complex Clifford algebras. And that's why you get more chiral cases than I would have said when I do it over the reals, right? That's the point. Okay. All right, so. No. No, it's brilliant. So like the spinor is, so what we're looking for, right, is a special representation of the spin group, which is a representation of the spin group but isn't of the orthogonal group. Right? That's what a spinor is. And each of these matrix algebras naturally acts on just a vector space. So this acts on R4, on H2, and so on. And the spinor is just an object in that vector space. That's its spinor components. So this would be a 4-component spinor with 4 real components. This would be a 2-component spinor with 2 complex components. And the point is that the spin group embeds inside the Clifford algebra. So when I make this action by the spin group, it will just act in the same way. So those things are representations of the Clifford algebra, and they become representations of the spin group. Sorry, I didn't say that very well before. Yeah, is that? Yep. So the spin group is the double cover. It's the simply connected group with the same Lie algebra. And you can always, the point is that the spin groups embed in the Clifford algebras. Yeah, and so once I have a representation of the Clifford algebra, I will get a representation of the spin group. And when we come to do supergravity, we'll find that we see gamma matrices all over the place. And so we're always seeing Clifford algebra actions really in the supergravity. So it's natural to think about representations of the Clifford algebra. Okay, so just one last thing. So there are some, so note that if we have the algebra, right, gamma m, gamma n is 2 eta mn times 1, you notice that gamma m transpose and minus gamma m and minus gamma m transpose have the same algebra. So in general, they should define, so they define equivalent representations. So in particular, you find that if D is even, then you can write minus gamma m as gamma d, gamma m, gamma d inverse. So this shows you how the representation generated by minus gamma m is the same as the representation generated by gamma n. Remember, two representations are the same if you can find something that intertwines between them, a matrix that takes one into the other. So that's what this one's doing. And you also find that gamma m transpose, it's usually written as minus gamma m transpose. There's some matrix C which takes you between the two of them. And if D is odd, then gamma D is in the center. So actually you just find that you get two sets. You get a set with the minus gamma matrices and a set without the minus gamma matrices. So you find that gamma m transpose can be written as some C gamma m C inverse. I'll put tildes on here. If D is 1 mod 4, and minus gamma m transpose can be written as C gamma m C inverse is D is 3 mod 4. Okay, so what I'm trying to say is if you have two representations of some group or something, these two things are equivalent if you can write one as some matrix times the other one, right? That just means the two representations are the same. So what I'm saying is that you could generate the algebra using these things instead, but they always give you the same, an equivalent representation. And the thing that takes you between the two equivalent representations, in the even case, it's gamma D and C, this matrix C. Just telling you it exists. In the odd case, things split so that you get gamma m and gamma m transpose together, or gamma m and minus gamma m transpose are equivalent, and it depends whether it's D is 1 mod 4 or 3 mod 4. Okay, I know it's a bit painful. The reason I'm telling you about this is that you can then define. You can always define an object which I'll call, so given a spinor, epsilon, right? Can always define an object which I'll call epsilon bar, which is given by the transpose of epsilon times this matrix C. And the point is that if I then work out gamma m epsilon and take the bar of that, that's just gamma bar epsilon. So this is actually just seeing these intertwiners. Maybe I'll call this, I won't call this, then it works in all cases, okay. And the point of that is that then you can define so that epsilon bar psi is invariant. So all I'm saying is that there's a natural, when you got the spinners, there's a natural object you can define that's going to be invariant under the action of the Clifford algebra. Does that make sense? Or the spin group. People use different notations for this. So, okay, now a word of warning. It's terrible doing supergravity because every single person uses a different assumption, conventions about what their spinners are, right? And puts eyes and don't put eyes, or like calls things different. Yeah, so it's horrible. So if we lived in a rational world, everyone would agree on the same convention, but I guess we don't. All right, and while I'm at it, why don't I just tell you, so how do you get the things? Do you remember all those families I gave you of going through different signatures and what the Clifford algebras look like? How do you get them? Well, there are some period relations. So you can show things like that if you take the Clifford algebra of PQ and you tensor product it with the Clifford algebra 0, 2, this is the same thing as the Clifford algebra, sorry, what am I doing? P0? This is the same as the Clifford algebra 0, P plus 2. And you can show that if you take the Clifford algebra 0Q and you tensor it with the Clifford algebra 2, 0, this is the same thing as the Clifford algebra of Q plus 2, 0. And the Clifford algebra of PQ tensor the Clifford algebra of 1, 1 is the same thing as the Clifford algebra of P plus 1, Q plus 1. So that's enough. By working out what the Clifford algebras are for small dimensions, that's enough to then derive all those other equivalences I gave to matrix algebras. So if you know those and you know things like that the Clifford algebra of 1, 0 is just R plus R, etc., some of the low dimension ones, then with those relations you can then derive everything else. Okay. So that's enough about Clifford algebras. I'm sorry to burden you with that. All right, so I wanted to now start a little bit about, yes?
So if you have sympathetic Majorana spinners,
Yep.
Clifford algebra elements are represented by quaternionic valued matrices.
Yeah, brilliant.
So your spinners are vectors which have quaternionic entries.
Yep.
So this invariant element is then a quaternion. Is that right?
Is then?
A quaternion.
Yeah, yes, in general it's a quaternion, yes. Yeah. Right. So, and I wanted to talk a little bit about supersymmetry. So I'm going to do it by thinking about, because I introduced this representations of the Poincare group. I'm going to do it by thinking about the Coulomb-Mandula theorem. So, what's the question? So the question is, can you extend the Poincare group into some larger symmetry group? So we're used to thinking of the symmetries of space-time as Poincare, and you know, in the 60s, people were wondering, like, well, we're doing lots of S-matrix calculations, and like you're wondering, like, well, is that all you could have? Like, if you just have a quantum field theory, is it possible that the symmetries, the space-time symmetries, are something bigger than Poincare? So, I mean, not just Poincare times something, but Poincare gets extended into a bigger group. And the Coleman-Mandula theorem says that for reasonable, well, for classes of quantum field theories, you find that the symmetry, so let's call this group G, you find that G is locally isomorphic to ISO plus 3,1 times some internal symmetry group. So the answer is kind of no. So what they argue is that all you can have is the Poincare group and then some internal symmetries. This locally, it just means globally you might have some funny things where quotients here also here or something, right? So, but locally that's what it looks like. Okay, so where does this come from? So there was actually like some earlier stuff. So there's actually a kind of simpler analysis by Rafferty. Which I only mention so that I can write the word O'Rafferty. So, no, not true. So that just looks at like, so basically what this did was to look at irreps of G. So the idea was to sort of see how could you, and with some, which has some Poincare subgroup. So the Poincare group has to sit inside some larger Lie group, and given thinking about all the ways it could sit inside, and then thinking about the irreps, do you get sensible errors? So are they sensible? So things like only 4 momentum operators. So you might just have something where you just have Poincare and then you just have some extra momenta that correspond to an extra direction, right? But that's not very physical. We'd see some other direction without having. And this analysis, basically, this also came to basically the same conclusion. So that was just a group theory analysis. It's just group theory. So it boils this down to a number of cases and then says which of them look sort of physically sensible. So it's not really a complete proof because you sort of put in a bit of physics at the end and you're just really just doing group theory of the analysis of particular, you're just doing group theory and looking at the irreps and then seeing whether you could make physical sense of them. So there are 1 or 2 loopholes in that argument. So then the full, for the full Coleman-Mandula, so I can confess to you, so, right, people always said Coleman-Mandula to me, and I never went and looked at what Coleman-Mandula did. I just assumed that it was something reasonable. So I looked. I didn't look very carefully, so you can fill in the details. But let me tell you what the basic idea is. So what did Coleman-Mandula say? So this was in 1967. So what did they assume? So it's written in a more technical way, but they're basically assuming a non-trivial S matrix based on a local quantum field theory. Okay. Relativistic quantum field theory. Relativistic gets in the Poincare group, right? So non-trivial S matrix, that just means there's some scattering, right? You can't just have particles come in and not see each other at all. And they have some scattering at all energies, technically. And then they make an assumption about the spectrum, which is that there are only a finite number of one particle, let me just say particles, of mass less than any given, less than m for any given m. So this says, like, as I go down in energy, there's only enough finite number of particle species below that, of mass below that. So in particular, this means there's a mass gap. This means that as you go down to zero energy, there must be some point where you go down in mass, there are no more particles of that mass. So there are no more massless particles, right? Okay, so these are the two assumptions they make. And the way the theorem works is to show that under those assumptions, that's outside, that would be outside this theorem, yep. So any conformal theory won't have a mass gap, I mean if it's non-trivial, and so like that is outside this theorem. And that's why you can extend the Poincare group into the conformal group when you're doing, right? Whereas this theorem says you can't extend the Poincare group. Okay, so what's the basic idea? Well, the basic idea is the basic idea is very simple. So let's draw some mass shells. So suppose we have some particles. I'm just going to draw some energy momentum. So suppose I have some particles. This is some mass shell, right? This is some m squared minus p squared is m squared. And then I might have, I can use colors. I might have another particle with that mass, and I might have another particle with that mass. But this assumption tells you that there's not a continuum of particles here, right? There's only ever finite numbers. So if I'm sitting at some particle with some mass and energy there, if I do an infinitesimal boost, I can move to some particle that's on or a translation, I can move to some particle state that's on the same mass shell. So if I do Poincare transformations, keep on the mass shell, right? If I do a Poincare transformation, if I do a Lorentz transformation, it keeps m squared the same. So you might ask, are there transformations in G that take you off the mass shell? So can you do something that moves like that, right? If you had a bigger group, you might expect that there are some infinitesimal transformations that move you off the mass shell from here to here, right? But if you have a Lie algebra, so infinitesimally, this is going to be infinitesimally. because it's got a continuous Lie group, so I can do an infinitesimal transformation. But the basic idea is very simple. If you've only got a finite number of mass shells, if I do an infinitesimal transformation here, it's not going to be enough to reach the next mass shell. So if my spectrum is discrete somehow, these transformations have to take the state here and map it to 0. They can't actually map it to the next mass shell. So the answer here is no, right? If the spectrum's finite. When I say finite, I mean in this sense. So that's the basic idea, is that once you've made this second assumption, you're kind of excluding transformations that take you off the mass shell. Now, what you really have to do is to work a bit harder. What you really have to, because you might have multi-particle states, and you have to think a bit harder about it. So what they actually show is that if you had such a transformation, then the S matrix, there would have to be a region of the S matrix would have to be trivial, or it would have to be trivial in certain region of momenta. And since we assume that we have a non-trivial S matrix, then that tells you that you can't have such transformations. Yeah. No. I think we're interested, so in the theorem we said locally isomorphic. So I think we're only interested in like the local geometry of the group. So we don't want to, I mean, a whole separate discrete factor, I agree you could have, but that's not what the theorem's about. It's about extending the Lie algebra, really, rather than extending the Lie. Yep. So it's by assumption we're looking at Lie algebras, and we're looking at infinitesimal things. Yep. Yeah. So there are some extensions to other dimensions. I can't remember exactly where that's at. I don't think it's completely proved. I don't think it applies to all dimensions. No, it doesn't. So think of it as a 4-dimensional theorem. Yeah. Yeah. What is this? Oh, because if you had, you could then have lots and lots of other mass shells right next to here, right? And then there would be an infinitesimal shift I could do. Yes, if you get rid of that, then it all, then yeah, it doesn't apply anymore. Okay, and then so then you can show that the group has to keep you on the mass shell, and then there's a second part, yes? Yeah, I mean, I suppose in principle, it could be that the group acts non-trivially here and then acts trivially here, right? So then you haven't excluded it completely. So I don't know. I take the point. This is the way they did it. You may be able to tighten that somehow, but yeah. So so that's the first step, and then the second step. So yeah, the first step's more subtle than I said, because you really could have multi-particle states, and what you have to think about there is really using some test functions and looking at like the scattering, they're looking at the S matrix, and the argument actually becomes that the S matrix will be trivial in some region, and you don't want that. And then the second part is to show that the only symmetries that keep you on the mass shell are Poincare times G internal, something that just factors. Okay. So the obvious question is then, how do you get around it? So how can we evade common mandula? So one possibility is, for example, to go to conformal theories. So that's violating the second assumption. But the other possibility is supersymmetry. So supersymmetry is interesting because it's a way of extending the symmetry algebra that intrinsically includes Poincare. So supersymmetry is a space-time symmetry, right? It involves Poincare. So how does that work? So the second case, so in supersymmetry, what we're doing is we're extending the idea of the symmetry group to include fermionic generators. So usually we think of the symmetry group as generated by some bosonic operators, right? Momenta, angular momentum, and so on. But in principle, you could have fermionic things that generate the symmetry group. And the structure is that you get, so we have, if B are bosonic generators, and F are fermionic generators, then what you have is you have something called a super Lie algebra. Right, so usually you have some Lie group and you have some Lie algebra. And the way the super Lie algebra works is that if you have, well, the commutator between two bosonic operators, a bosonic operator, that's like the ordinary Lie algebra bit. Then you can take a commutator between a bosonic and a fermionic, and that will look like something fermionic. And then you get the anti-commutator between two fermionic things, and that looks like something bosonic. So this is the anti-commutator. So this is an algebra that's, a mathematician would call it a graded algebra. So if you think of like bosons as having like a kind of even charge and fermions having an odd charge, this is even times even is even. Even times odd is, oh, that's terrible. Oh, even plus even is even. Even plus odd is odd. Odd plus odd is even. And what does it look like? So let me just tell you what this algebra is. So there's a super Poincare algebra that extends the Poincare algebra. So one can extend the Poincare algebra to super Poincare in the following way. So we start with the commutators of Poincare. So that involves PM and MN, which we wrote down before. Let's just say we're going to be in d equals 4, and I'll use Cliff 3.1, which is like M4R. So I'll use Majorana spinners. So I have 4-component Majorana spinners, right? And then what other commutators do we have? So we have the Bose with Fermi. So PM, so I'm going to have some new Fermi operators, which I'll call Q, alpha. So I'm going to have spinners which are labeled by an alpha, where alpha runs from 1 to 3, 4, right, across the 4 components. So these commute. So these new operators Q, the super translations, or the supersymmetry operators, commute with momenta. With the generators of the Lorentz group, they transform like spinners. This just says that they transform as spinners under spin 3.1, right? That's the infinitesimal transformation of a spinner. It involves the gamma matrices. And then the interesting one is that there's an anti-commutator between this one and this was this conjugate, this was this transpose thing that I could always define. And that looks like the following: -1/2 gamma m alpha beta PM. So I've introduced some new fermionic operators. They transform as spinners. That's a bit like spin statistics, right? If things are fermions, they better transform like spin half. And this just says they transform like spinners. And here's the interesting one. If I take the anti-commutator between these two Q operators, I get a translation. So this is the sense in which it's a non-trivial extension of the Poincaré, right? Because I've got some things which, when I take them together, I get a translation. Okay. So that's the supersymmetry algebra. It's an extension of the Poincaré algebra. And there's a corresponding theorem. Where am I going? So many of you have probably seen that before, maybe in different notation, but some of you haven't if you've never seen supersymmetry. So there's then a corresponding theorem called the Haag. I have to remember how to spell. Yes. Theorem, which says G, so for superalgebras, so if I'm allowed to extend my symmetries to include fermionic bits, you get the same result. G is locally isomorphic to super Poincaré plus some internal symmetry. So basically, you can't do anything more than this, right? Even if you allow superalgebras. Actually, this is provided you allow, but I guess with, maybe I should say, with multiple supercharges. So what do I mean by that? So I could have Qi, where I is running from 1 to up to some n. So I just had a single supercharge there. In general, you can have multiple ones. So let me tell you what happens when you do that. So this is the algebra I wrote down there is for n equals 1. If n was not equal to 1, I would put an I index on here. I'll put an I index on here and an I index on here. I'll put an I index here, a j index there. I'll put a delta ij. And then something extra can happen. I can have a c alpha beta and then some z ij. And the z ij has to equal minus z ji. And this is called a central charge. So in general, I could have more than one of these objects. And when I do that, the algebra extends slightly, and I'm allowed some things here which are just abelian things. So there's some new bosonic abelian operators. They just commute with everything. So in general, we label superalgebras by this number n. So you might see 4D n equals 1, 4D n equals 2, 4D n equals 3, 4D n equals 4, right? That's just how many supercharges you have. Yeah.
How do you determine what the communication of the qubit is actually for a qubit out of supercharge? I can see like combination of qubit like n.
This one follows from the fact that Q is a spinner, yeah. So how do you get this thing? Well, so there's various things. So to make a sensible algebra, you certainly have to have Jacobi. So you have to make sure that this satisfies the proper Jacobi relations. And so you can analyze like general super Lie algebras in the same way that you can ordinary Lie algebras. So you've sort of got a problem if you like take a super Lie algebra and ask what you have to have the Poincare algebra sitting in it, what's the possibilities for that? Actually, this comes about by, yeah, that's probably so that would be the sort of abstract maths problem that you would want to do. Yeah, yeah, yeah.
Just make sure I've got it correct. Is the fact that you have the generators that transform into spinners forced upon you in some sense? In the sense that I could write down some sort of gradient in the answer where my things in grade 1 aren't necessarily spinners.
Yes.
There are some things that are forcing you to make these spinners.
So I'm wanting it to be some non-trivial extension of Poincare. So if I took them to be just scalars or something, then the anti-commutator is never going to give me something that looks in Poincare like P or M. So it's the fact that I want it to be an extension of Poincare algebra that means I want them to transform non-trivially in the under Poincare itself. But yeah, you could, in general, there's a more general question that but this is the thing that appears physically and is the most general thing you can do physically consistent with quantum field theory. Yeah. Yeah.
Do the relation for the Q bar are the same under Q's?
Okay, so my Q bar here is just Q transpose times C. So there's no complex conjugation going on. So there's only one anti-commutator, which is, I've written it as a bar, but you can think of it as, I'm doing it in a Majorana basis. It's not a Q and Q bar are not independent in that sense, yeah. Yep.
What does exactly mean? It's like gamma.
It's this thing that takes me between these two forms of the gamma matrices. And it's appearing because I've got actually the way I've written it here, yeah, it's appearing because of the way I defined this object. Yep. But in 4 dimensions, it's antisymmetric, and that's what means that this thing has to be antisymmetric. Is that okay? Any other questions? All right, so okay, let me just right. How are we doing for time? Okay, so just to say, often the supersymmetry algebra is written using the chiral spinors, which come from, in my language, the even part of this looks like M to C. So these are two-component complex spinors. So for example, if you look at the classic book by Wessenberger or many other books, that's typically the way the algebra is written. And so we can call these things, I'll call these things curly Q. And roughly speaking, there's a relation where this curly Q I can think of as a projector, right? A chiral projector on the Q. I'm defining where this projector is something like 1 plus I times gamma 4 acting on this guy. And I can define a Q bar, which I naturally define as the bar of this guy with the other projector. And then you can rewrite the algebra in terms of Q and Q bar. So this is just taking this real spinor and splitting it into a vial, into two vial spinors, right? And the only reason I mention that is because it's easier to see there so it's then in this basis, it's easy to see that the n extended, so I mean for some general n extended SUSY algebra has a automorphism symmetry where you take these Q's, and now I've got I of them, and I rotate them. Yep. So what I mean by that is when I write gamma D, I mean gamma 1, gamma 0, gamma 1, all the way up to gamma D. The product of all of them is totally symmetrized. Sorry, any other questions? Yeah. Oh, yeah, probably. Yeah, I probably need a half here, right? Because it squares to so that it's a proper projection. Yep, that sounds right. So there's a symmetry where you rotate these, and this R is in general an element of UN. So if I've got n supercharges, I can rotate them into each other. This is called the R symmetry. It's still an automorphism of the algebra written that way. It's just a bit harder to see because I have to put in all these projectors, right? But it's still there. If you want to understand where this is just a unitary group. If you want to understand where this is coming from, you can think about it in terms of, again, this even Clifford algebra, right? These were complex. So if I have some objects which are complex objects, there's a norm on them which is naturally preserved, which is preserved by the unitary group. So UN preserves a norm on complex objects. So it's because of this delta that appears here. That's like a norm on the IJs. This is this delta IJ. So I want something that preserves the delta IJs, but acts on spinors that are complex objects. That's going to be a unitary group. If this spinor group was a real thing, then I'd want to preserve the delta IJ with an action on real objects, and I'd get an orthogonal group. If it was quaternionic things, I'd want to preserve a norm on quaternionic things, and I'd get what a mathematician would call a symplectic group, what physicists usually call a unitary symplectic group, USP something. I'll probably mention that later on. But that's where this symmetry is coming from. You're needing to preserve that delta, and the objects that you have, thought of as spinors, honest spinors of the spin group, are complex things, and so you're preserving some complex norm. Okay. And in general, if you take, there are extensions of superalgebras to other dimensions, and they will always have some kind of R symmetry that will be based on whatever kinds of objects are appearing here. Okay. All right, so now let's just do what we did before, or maybe we should. All right, why don't we stop and have a break there? And then when we come back, we'll look at the unitary representations of this algebra, just as we did for the ordinary Poincare ones. And those are going to tell us how we can build supersymmetric theories. Is that okay? Okay. So, I don't know, 5 minutes or something, 10 minutes? How long do you usually have? 10? Okay. So I'll see you at 5 past. Okay. Okay, so given we've got this algebra, then the thing we should do is ask how can we construct physical theories. So then we're again interested in what are the unitary representations of this now super Poincare algebra, right? So what they give you are things called supermultiplets. And what happens is that this Q operator relates particles of different spin. So let me just do some examples. So for example, we can have something called the chiral multiplet. So that's a Hilbert space that's built out of a pair of one particle Hilbert spaces. So let me take something of mass m spin 0 and something of mass m spin a half, and it has to be the same mass. So I'll call this field Z of x, and I'll call this field chi of x. So remember, this means that the mass zero field is going to satisfy some Klein-Gordon equation, and the mass and the spin a half field is going to satisfy some Dirac equation. And remember, in general, we're doing Hilbert spaces, right? So these are kind of complex objects. So then, so for e.g. Translations, right, if we're interested in the change in the field x, so if we do a translation by some amount am, so I'm translating by some amount am, infinitesimal amount, the change in the field is going to be given by, well, if we think of things as being Hermitian operators, I act with the thing that generates translations by an amount, and I use an amount am, acting on, say, the z field. And this is just given by minus am times the derivative of z. It just shifts the argument of z, and then I expand. Is that okay? You're used to thinking about the symmetry operators like that? Okay. So what if I do a supersymmetry transformation? So for the Q's, I need a parameter, a spinor parameter, which I'll call epsilon alpha. And it also has to anti-commute, because the Q's anti-commuted. So I have some spinor, which is a set of numbers, but I have to think of them now as anti-commuting numbers. That's slightly weird. You just have to remember that everything anti-commutes. And if I act on the Z, so what are the supersymmetry transformations? So I act on the Z. This is now, I'm going to act by something that looks like epsilon bar Q acting on Z. And what is that equal to? Well, I find that it's equal to 1 on the square root of 2 epsilon bar P left, that's that same projector that I had before, acting on chi. And if I do the variation of the spinor field, I find that I get minus 1 on root 2 P left acting on gamma m dmz minus m z bar times epsilon. So sorry, I'm wondering if I just made it right. So the supersymmetry, so the Poincare symmetries keep me within Z or chi, and then the supersymmetries move, the change in Z depends on the spinor, and the change in the spinor depends on the scalar. So that's why I have to have both spinors and scalars if I want to have a supermultiplet representation, okay? So this is something that has spin 0 and spin a half. Let's do, so you can analyze all the multiplets you get. Yep. Mm-hmm. Say again? This is a complex scalar field. The G bar is just a complex kind. Epsilon bar is indeed, oh sorry, epsilon bar is epsilon transpose C. Yeah. Sorry. Okay, and then, sorry, I'm totally worrying myself. What am I doing wrong? Okay, you could also do a vector multiplet. So let me say example. Vector multiplet. So now I do, let's take something, so this is, I'm trying to do like a gauge field. So let's take my vector multiplet Hilbert space to be a massless thing with chiralities plus or minus a half, and with and a massless object with helicities plus or minus a half, and a massless object with plus or minus 1. So this is going to be like the gauge field with two polarization states, and this is going to be a massless fermion with two spins. So now I'm going to have, so I'll call this guy, I'll call this guy lambda. Is that what I want to call it? Yeah, I'll call this guy lambda of x, and I'll call this guy am of x. And I'm going to have the equations that gamma m dm lambda is 0. And I'm going to have that dm fmn is 0, right? That's the wave equation for the gauge field. And then again, I get supersymmetry transformations that relate them into each other. So when I do the variation of this gauge field, it looks like minus a half epsilon bar gamma m lambda. And when I do the variation of the lambda, I get something that depends on the field strength. So again, I get transformations where the boson depends on the fermion and the fermion depends on the boson. And you can check that when you make those transformations in these field equations, it takes one field equation into the other and vice versa, right? Okay. So let me do one more. Yeah. This one? No, I'm gone back to my Majorana things. Everything is just real things. But because we're looking at, yes, so we're looking at the unitary representation, so our things are complex solutions of wave equations. So Z is a complex thing. So no, it's absolutely fine. It's absolutely, no, you're not getting lost. I mean, the fact that this is written in terms of P left, it might be more natural to use the curly Q. Yeah. You can write everything either using the Majorana spinner or using the chiral spinner. When I'm looking at just Hilbert spaces, all my solutions are complex solutions, even though the algebra is a real algebra, right? It's a real algebra because I erased it, but there's no i's anywhere in that algebra that I wrote down. So I'm looking at representations of a perfectly sensible real algebra. I can use complex objects to represent a real thing, and that's kind of what I'm doing here. If you wanted to, you're absolutely right that if you wanted to write this in a more natural way, I would use the curly Q's here. And these P lefts are coming in because I'm trying to write things in terms of the non-curly Q's. Yeah. So if I wrote it in chiral spinners, it would look much simpler. Yeah. But it's good. Yeah.
Then
Yeah.
here, right,
Yeah.
Then here chi and z forms another multiplet, and br chi and z forms another multiplet.
Yes, so good. So if I went to the massless case, this thing decomposes into two irreducible Hilbert spaces of plus helicity and minus helicity. And the Z I can split into Z and Z bar. And Z goes with one helicity and Z bar goes with the other helicity. Yes, that's exactly right. And here too, actually, I could decompose this into plus a half and plus one and minus a half and minus one. And if I did that, I would take, so actually we have two helicity irreps. So this representation is strictly speaking reducible. It reduces into the two helicities. So one where I take lambda left and I take p left of lambda, and I take with that f plus mn, which is the thing which is the self-dual field strength. Probably, I hope my conventions are correct. So I can split this if I want into plus left, p left and self-dual, and p right and anti-self-dual. And actually this thing really decomposes into two different irreps. But I'm just keeping it as one. Yep. And then while we're at it, why don't we do, there's a kind of graviton multiplet, by which I really mean just spin 2. So what do I do there? Well, I take massless spin 3 halves and I combine it with massless spin 2. So this is this field, this Rarita-Schwinger field that we talked about already. And this is like some linearized metric, right? Some sort of spin 2 field. And I know what the equations are, so I'm going to have some gamma mnp dn psi p is 0. And here I get the equations of linearized gravity, which see this Leshnerowitz operator. So I have to write down a whole load of indices. So that's the linearized equation of spin 2, massless spin 2. It has a symmetry. So remember, this one has a symmetry and this one has a symmetry of symmetrizing on those indices. This is like the remnant of diffeomorphism symmetry, a coordinate reparametrization. And then there's, where am I going? So then, and there's with some supersymmetries where the change of the linearized metric looks something like this. Sorry, what am I doing? And the change in this guy is something that I am not going to write out, but there's some combination of h's. We'll come back to that. So again, you can show that under those transformations, these two equations switch into each other. So we're beginning to see the origins of supergravity. We might ask, is there a way that we could take this multiplet and promote it into some big interacting theory where this becomes not just the linearized graviton around flat space, but becomes the full gravity metric? And what would we have to do with this field? And interestingly here, this theory already has sort of something that we know from the gravity point of view as the remnant of local coordinate transformations. And this guy has some symmetry that depends on derivative of a spinor parameter. Maybe I shouldn't call that epsilon because it's nothing to do with the a priori it's nothing to do with the supersymmetry parameter. So this looks something a bit like if we made supersymmetry local so that this thing depended on position. Okay. Yep. Yeah, so everything I'm doing here is just for n equal 1. And you can do the same thing for n equal 2 and n equal 4 and so on. And you get, in general, bigger multiplets. So, yeah, so as you have more supercharges, you get to relate more and more fermions and bosons. So, for example, if you have n equal 8, the spin 2 multiplet has spin 2, spin 3 halves, spin 1, spin a half, and spin 0 in it. Yeah, yeah.
Is this the only way to combine supermultiplets, going from like boson with spin n,
Yeah.
and then coupling with the boson with spin plus 1?
So for n equal 1, so you can do an analysis of the super algebra and try and work out what the representations are. It's not too bad. And yes, for n equal 1, you'll always get something, you'll get two fields which differ by a spin of a half. So you'll get 2 and 3 halves, or 3 halves and 1, or 1 and a half, or a half and 0. And that's roughly speaking, there'll be a sort of, the Q's act like ladder operators. There's one Q that sort of reduces the spin and one that increases the spin. And so if you only have one Q operator, like I have here, you can only reduce the spin by 1/2 unit. If it was n equal 2, I'd have two Q operators that would allow me to reduce the spin by 2/2 units. So the multiplets get bigger. I'm not sure if I'm making sense.
So does the Q operator, like this ladder spin operator, mounts from one from another spin and then it goes to 0, or is that like
So no, so say we have 2, 3 halves, 1, a half, 0, minus a half. I mean, you could, let's just think of it like that for the moment, right? So if I go to, in the same way that when you do the analysis of the Poincare group, you want to go to some frame where everything's at rest. So I go to that frame, and then I can decompose my Q operator into sort of two things. Let me call it Q plus and Q minus. And Q plus tells me in that direction, and Q minus sends me in that direction. But I have, if n equals 1, I sort of have that Q plus squared is 0, and Q minus squared is 0. So, so what happens is that I either get a multiplet that's just 2 and 3 halves, and then if I do Q minus again, it vanishes. Or I get a multiplet which is like 1 and a half or something, and then the next one vanishes, or 3 halves and 1, or so on. If I have more supercharges, then I can have Q1 plus and Q2 plus. And now, so if I had two supercharges, I could now do it twice, and I get multiplets that have spin 2, spin 3 halves, and spin 1. So it's like it's very like the way you do, in a very simple way, it's like the way you do SU2, where you do any representation theory with some raising and lowering operator. Okay. So having spin 1 and spin... no, it is. What happens when you do the interacting theories is that the moment you put the spin 3 halves in, you kind of have to put the spin 2 in as well to make it a full interacting theory. So, yeah. So just to say that, so what I've given you here, so these are the what's called on-shell multiplets, right? So what I mean is that they satisfy free free wave equations, and they're really just they just label the allowed Hilbert spaces. Right, I set up this problem as asking what are the representations theory, and those are what those Hilbert spaces are, right? So in quantum field theory, the same fields / representations appear, but now as, if you like, even classical fields, not Hilbert spaces, not elements of a Hilbert space. Right, so the Klein-Gordon equation, I could think of it as a classical field, or I can think of it as defining a Hilbert space of one particle Hilbert space, right? So in the quantum field theory, we see the same kind of representations, but we now want to think of them as classical fields that we're then going to quantize. So, and in general here, you have interacting theories. So this tells you that they're no longer free field equations. So we really want to kind of relax our representations so that we're not necessarily stuck on the free field equations. We still have some sort of supersymmetry that takes fields into each other, but we don't want to impose these nice field equations. We might want to have some nonlinear equations. Okay. So say again? Okay, so what I'm saying is that I've thought of these fields as being things that tell me about states in the Hilbert space. If you really do the quantum field theory, there's a way in which fields appear quite independently of that, which is I start with some classical field theory that I quantize. But they're actually the same kinds of representations that appear because I'm still doing Lorentz invariant, I'm still doing Poincare invariant things. So the Klein-Gordon equation could be telling me about states in the one higher particle Hilbert space, or it could be the classical Klein-Gordon field. But for that, the latter case, you want to write in interactions. So I want to have some phi to the fourth interaction or something. That will no longer have the same field equations as the ones I wrote down, the classical Klein-Gordon equation. So that's what I mean by going off shell, is that I want to sort of drop the free field equation and allow myself to generalize it to have interactions. That's all I'm trying to say. So, so you can do this for the supermultiplets. So for example, for the chiral multiplet, you can introduce what's called a superpotential. W of Z. So I then have an action that looks something like dmz, dmz bar, and I have some chiral. And then here I have something like W prime, W bar prime, and then I have some chi bar, P left. Again, this would look much simpler if I used the chiral representation, but I'm using the Majorana one, where I've now fixed some function, holomorphic function W of Z, and I get kinetic terms, and then I get something that looks like a potential term for Z, right? This is going to be a function of Z, this will be a function of Z times a function of Z, and W prime is just a derivative with respect to Z. And sorry, these are double primes. And then I also get something that's an interaction between fermion, fermion, and boson. So this is looking like some kind of Yukawa interaction in general. And this thing is still supersymmetric. So I can still make supersymmetry transformations of this theory if I take the boson transformations don't change, but the fermion transformations get a term that depends on W. Okay. So my equations of motion have now changed because they now depend on this function W, but I still have some nice supersymmetry transformations that take equations into equations. Yeah, sorry. It's a way of generating a potential in supersymmetry. I think that's kind of where the word comes from. And the key thing is this is a funny potential, right? A general potential would be a function of Z and Z bar. It could be any function of the scalars. This is a function which is W prime of Z times W prime of Z bar, so it factors into these two things. So only when the potential takes that form and you have precisely this interaction is the whole theory supersymmetric. So what's happening is supersymmetry is really constraining the allowed interactions, which is what you'd expect. You've got a new symmetry, and so it tells you you can't have completely general interactions. Yes? Is there an analog in the Poincaré? So yeah, in Poincaré, right, you would just say, oh, I have a Klein-Gordon field. I could write any potential, and I would still have the Poincaré symmetries, right? It wouldn't satisfy the Poincaré equation, that wouldn't satisfy Klein-Gordon anymore, but it would still realize the symmetries, yeah. So that's the sort of analog. It's just taking an arbitrary potential here in the Poincaré case. In the super case, I can't take an arbitrary potential. I have to take one that factors properly. Yeah. Sorry, there was a question here and then. Yeah, go ahead. So Z was there were two fields. There was a complex scalar field Z that originally satisfied the Klein-Gordon, and there was a spinor field chi. Yep. Yeah. Oh, sorry, this should be epsilon. Would have a right projector. I know what you're saying. I think it's okay, but let me think about it before the next. Yes, and then yes. Sure. I don't know what order it was. Yeah.
So I wanted to ask, what is the measure integrated working? Because now we're working with small z and zr, which are complex coordinates, if I'm not mistaken, and how does they tie to our space-time?
Sorry. Yeah. Good. So this is just an integral over 4 space-time dimensions. Z is a field that depends on the space-time dimensions, which is just a complex field.
So we do derivation with respect to the field of the superpotential.
Yeah, so they're here. I'm thinking of the superpotential as a function of the field, which is a function of space-time. Yeah, good. Yeah. Okay, so there's a whole other story that I'm not telling you about, which is how can you write down general supersymmetric interactions for n=1 field theories. And there's a very beautiful way of doing that using something called superspace. So I'm kind of putting that to one side, and by using superspace, you can understand the most general interactions you can write down. Yeah, and in fact, this is not yet the most general. I can also do something that changes the kinetic term, which uses something called the Kähler potential. So, but I just wanted to point out to you that you can generalize these things. And since I still haven't talked about supergravity, I thought I should not say too much about it. So for us, what we're going to be interested in is so let me just say something about towards supergravity. So the first sort of question is, can we extend the graviton multiplet so HMN becomes the full metric I guess I put add interactions. So the graviton multiplet was a free multiplet, right? Just had a free wave equation. In the same way here, we've started to put in interactions. Can we add in interactions to the graviton multiplet so this becomes the full metric? And we get gravity. And a related question is, can we make supersymmetry a local symmetry? So instead of having, so epsilon, the parameter, now becomes a function of space. So all the supersymmetry transformations I wrote down before, this was just some constant spinner. Can I now make it like a local symmetry where it depends on where I am in space-time? So both these things are what lead you to supergravity. And let's just think about the second one for a moment. And then we should stop. So in the algebra, we had that the anti-commutator of Q's looks something like P. So if epsilon becomes local, this is local, their anti-commutator will be something local. So I'm going to have to do local translations. This is going to imply that I have to have local translations. And I'm forced into it just because of the form of the super-Poincare algebra, precisely because the super-Poincare was an extension of the space-time symmetries. But what are local translations? Well, that's like saying x mu maps to, or change in x, or let's say x mu goes to So xm goes to xm plus some am, where now this depends on x. But this is just a general coordinate transformation. So we see that local supersymmetry implies diffeomorphism invariance, or diffeosymmetry. Right, this is general diffeomorphisms, right? But this is like, i.e. gravity. So you know that to write down theories that are symmetries of general coordinate transformations or that have a diffeomorphism symmetry, you're pushed into doing gravity. So the only way we can do the second thing, make SUSY local, is actually by doing gravity. So these two stories go together. So trying to make the gravity multiplet into a full supersymmetric thing is the same story as trying to make supersymmetry a local theory. So that's going to be the big question. Can we find some way of writing down a theory which has local supersymmetry, and such a theory will necessarily be a gravitational theory? So whatever this theory is, this is what leads us to the theory called supergravity. And what we're going to expect is it's going to be a theory of a spin half and a spin 2. It's going to have spin half in it because it's going to have global supersymmetry as a limit, so it's going to have spin 3 halves in it. But it's going to be some complicated interacting thing where the spin 2 becomes the graviton, the full graviton, and we have to ask what happens to the spin 3 halves. Okay, I guess I should stop there. Thanks.